As you may recall from earlier in the course, there's another problem we like to ask about graphs or networks called maximum independent set. An independent set is a set of vertices where no two neighboring vertices both belong to the set. They must not like each other very much. They have to be at least 2 steps away from each other in the graph. Now, we could add weights on these, but let's say each one is worth just 1 unit. The maximum independent set problem is, well, what's the biggest independent set you can have? For instance, on a checkerboard, we could take all the black squares and take half the vertices. But if we had more connections, then we couldn't have that many, perhaps. So if I show you a graph, how many vertices can you pack in so that none of them are neighbors of each other? So this is kind of interesting because it's an optimization or maximization problem. And remember that we like to think of problems in NP as decision problems or yes or no questions. So we're going to do a little sneaky move here. And instead of just a graph as input, I want you to give me a graph and an integer k. And then the challenge to me is the yes or no question. Is there an independent set consisting of k or more vertices? We'll get back to this later. Obviously, this is almost the same question, but by making it yes or no, it makes it a little bit easier for us to think about. Here's a quick proof, a very quick proof, that this problem is NP complete. On the left here, I have a little graph, a pentagon, and I've colored it with 3 colors, which, by the way, I need. On the right, you can see that I've expanded each vertex of the pentagon into a little gadget. And if you check it out, you'll see that in that little triangular gadget, I've chosen a vertex that corresponds to which color I used to color the corresponding vertex of the pentagon. I've drawn a bunch of parallel edges between these gadgets, and then the independent set rule, that no 2 neighbors can both be included, corresponds to the rule that we have to have different colors on our different neighbors. Finally, since this pentagon has 5 vertices, we will demand an independent set consisting of 5 vertices in our gadget. That forces us to actually give every vertex a color. We're done. Frankly, we could do a more formal proof if we wanted, but I think you see the idea. This lets us translate any graph into another graph. Let's say we're translating a graph G into a graph G prime, such that G prime has an independent set of a certain size if and only if G is 3 colorable. Bam! Independent set is NP complete. I promised you Hamiltonian path. I'm almost going to fulfill that promise. It's actually a lot easier to show NP completeness for a directed version of Hamiltonian path where the edges have arrows and where the tour, the salesperson, is required to move with those arrows. Again, we need variable gadgets and some kind of constraint gadget. I'm going to reduce directly from our old friend 3-sat. Here's how it works. You can see we need to start at that top vertex because the arrows are only coming out of it, and we need to get down to that bottom vertex because the arrows are going into it. Somehow we need to visit every other vertex on our way. Well, look at this top gadget here. It has a kind of chain of vertices across it. You can go across this chain this way or that way. But the rule is, remember, we have to visit each vertex once and only once. So if you start this way crossing the chain, you can't turn around. That means we have to traverse this gadget like that and then down, or like that and then down. Well, we will arbitrarily decide that this corresponds to setting that variable x true or false. Those are our variable gadgets. They're a way to express a choice of which way we go in the Hamiltonian path problem. Well, how do I add a clause that demands, for instance, that x is false or y is true or z is true? I only need one more vertex. I add that off to the side, and then I allowed optional detours from these bridges to that vertex, but in a way which only works to cross the bridge in the direction consistent with the value of the variable that that clause would like. So for instance, if you're traveling across this x gadget from right to left, corresponding to setting x false, you may, if you wish, make a detour and cover that constraint gadget and then continue on your way. Or you could do it when moving left to right in the y gadget, setting it true, or with z. So again, if you have a 3-sat formula with a bunch of variables, we would have a bunch of these gadgets with a bunch of clauses, a bunch of these little detour vertices, and we're done. We've proved that the question of whether I can get from the top of this graph to the bottom and touch every vertex along the way can express any problem in NP, because it can express 3-sat. So there's a little extra work which I don't have time to show you, which lets us remove the arrows and turn this into a question on undirected graphs. It's just another gadget. You might enjoy thinking about it if you wish. You just need to figure out how to simulate edges with arrows using edges without arrows. I'll leave that to you. But I claim that at this point, I've given you a lot of evidence that telling whether a graph has a Hamiltonian path might be very hard, because if you can do it in polynomial time, all of these problems can be solved in polynomial time. Yet another NP-complete problem I could tell you has to do with playing with wooden puzzles. So at your favorite winter solstice holiday, your friend gives you a big bag of pieces of nice artisanally constructed rosewood that has been cut into all sorts of different shapes. And your job, if you can, is to fit them together and nicely fill out a tray which has yet another shape. I don't know about you, but I like puzzles like this as long as they're not too hard. So this type of problem is also NP-complete, which kind of makes sense because you know that these problems can be hard. The proof is very easy. Here are two shapes of tiles. This one is a little elbow-shaped tromino. I call it a tromino because it's made out of 3 squares, like dominoes are made out of 2 squares. And then this little 2x2 tetromino made out of 4 squares. Well, the general question then is, if I give you a shape, can you fill it in with copies of these 2 tile shapes without any gaps or overlaps? Well, that's NP-complete. Here's the proof. Here's how to build a computer out of them. You just kind of need to doodle a little bit. A lot of NP-completeness proofs consist largely of doodling. We need some kind of wire. And if you look at these channels, you can see that with the elbow-shaped piece, there are basically 2 ways to fill in that wire. One where the elbows are kind of marching this way, and the other where they're marching this way. Fine, that could mean true or false. We then just need to find some way to have a junction which corresponds to an AND or an OR gate. We need to make sure our wires are kind of flexible and we can connect things to each other. We need a place where the wires can begin so that that variable is set either true or false. And finally, we need a way to demand that the output of the circuit is true, which is this little tail at the bottom, which has to be filled in with an elbow. There you go. That's the proof. And that's partly why these tiling puzzles are hard. So, lest you think that all of NP-completeness is about problems in what we might call discrete mathematics. Integers, whole numbers, graphs, things with nodes and links, tiles made out of squares, colors. Well, in fact, NP-completeness shows up in nearly every branch of mathematics, even continuous mathematics. I wish I had time to prove to you that telling whether this integral is non-zero is NP-complete. It's just the integral from minus pi to pi of the product of a bunch of cosines. And these constants in front of x, the a1, a2, and so on, those are the inputs to the problem. So those are going to be integers. And then The product, the integrand, is some wildly oscillating function, and the question is the integral 0 or not? Is the area above the x-axis exactly equal to the area below the x-axis so that it all cancels out, or isn't it? That's NP-complete. So NP-completeness is lurking even in areas of mathematics that at first glance have nothing at all to do with simulating computation. We've come all the way from Boolean circuits and chips that are checking solutions to problems to integrals. So NP-completeness is really a kind of ubiquitous phenomenon. So by chaining these reductions together, we can build an entire family tree of NP-complete problems. Let's review. We started with this very basic question of whether a solution to a certain problem exists, which can be checked by a program in polynomial time. Since programs can be turned into Boolean circuits, that gave us circuit sat. Since those can be transformed into satisfiability formulas, that gave us 3sat. And so we can build this branching tree by reducing one problem to the next, getting us to Hamiltonian Path, NAE-sat, problems about tilings, problems about adding integers together. And in fact, there's a famous book by Gary and Johnson. It's quite old, decades old, but it contains thousands of different NP-complete problems. This tree doesn't just include things having to do with Boolean logic and graph theory, but also things involving calculus, as we saw, whether integrals are 0 or not, whether we can schedule airplanes, lay out components on a chip with a certain amount of wire, and so on. And remember that either all of these problems can be solved in polynomial time, or none of them can. Either they all have some miraculous insight comparable to what Euler had for his problem about Eulerian tours, or none of them do, and they all require something like exponential time and exhaustive search through a vast haystack of possible solutions. You should also keep in mind that each one of these problems is an example of solution existence. So in fact, you should view this tree as having loops that go back into the root and loop around, so that any of these problems can be transformed into any of the others. They are all either easy or they're all hard. And it's kind of hard to believe that they're all easy. Every single one of these involves some complicated nonlinear relationship, a set of constraints, something that we're trying to optimize, involving either discrete or continuous variables. And it's really hard to imagine that none of them require exhaustive search. So indeed, the majority view, the consensus, except for a handful of heretics, is that all of these problems require exponential time, and that NP is really a larger class than P.